This is Lecture 3A for Calculus 1, Secants, Tangents, and Derivatives. Consider the slope of a straight line. We could calculate it as m equals, some people say rise over run. You could say delta y over delta x. Greek capital letter delta means change, usually big change. So the change in y is y2 minus y1. The change in x is x2 minus x1. The points x1, y1 and the points x2, y2 were any two points along that straight line. Once I have calculated the slope, it is good for every point along the straight line. Now think about a parabola. If I want the slope along the parabola, I have two problems. The first problem is that the slope is different at every point along a parabola, and the second is that I don't know how to calculate it. Here, for example, is that parabola. You notice that for all values of x less than 0, the parabola is the red line. Well, the slope is increasing along the parabola if x is less than 0. If I'm over here where x is greater than 0, the slope is decreasing. And right at 0, the slope is 0. Okay. I want to compute the slope, say, at a point right here along this parabola. I don't know how to do it, so I do what I know how to do, and that is to take a straight line slope. This is the equivalent of using whatever tools are in your toolbox. You know, if you've got a claw hammer and a Phillips head screwdriver, I guess that's what you're going to use. Or if you look in your sewing box and all you've got is some straight pins and a couple needles, well, and you need to get the job done, then that's what you use. In this case, I know how to compute the slope of a straight line, and so that is what I do. To compute the slope of a straight line, I need 2 points. So first I have my point of interest here. I pick another point over here, and I use the formula for the straight line slope, and I calculate the slope. I can draw a line between those 2 points. That line is called the secant line. Obviously, it is not a good approximation to the slope at the point over here. Okay. So I can refine the secant line. I can refine this approximation, and the obvious way to do it is to pick points closer to my original point of interest. So I could start here, and I could compute the slope of a line going through another point. Well, that's a little bit better, so that gives me another secant line. I could try this line, where I've chosen a point here that's closer to my original point of interest. So what I'm doing here is creating a sequence of secant lines, each with its own slope. And I'm letting the corresponding point get closer and closer to my point of interest. Looking at the formula here, that would mean that x2 minus x1 is getting smaller and smaller. I cannot let x2 equal x1 though, because I would then be dividing by 0. But I have another tool I can make use of, and that is the limit. I can take the limit as x2 approaches x1 and see what I get. I'm going to draw another curve through here for that process. You've probably heard of a tangent line, and there's various definitions of them. But here's a definition of this tangent line. I'm going to write T here for tangent line. A tangent line to the curve at this point of interest intersects the curve at that point and has the same slope as the curve does at that point. So by taking the limit, all these secant lines are going to turn into, or the limit of these secant lines is going to be the tangent line. The limit of the slopes of the secant lines is going to be the slope of the tangent line, and that is going to be the slope at that particular point. So now I'm going to repeat this whole process with words. I want to find a method for computing the slope along a non-straight line. The only tool I know is the straight line slope. So I use it in the following manner. I'm going to pick a particular point here. I'll call it minus 3, and it is along that particular parabola that we saw before, minus x squared plus 6. I can visualize this slope by drawing a bunch of straight lines that go through the point of interest, minus 3, and has and this point, this particular line will have the same slope as a curve at that point. I call that the tangent line. So I visualize the slope by drawing a straight line that goes through the point of interest, minus 3, and has the same slope as a curve at that point. That will be the tangent line. I can't calculate that tangent line right away, but I can calculate secant lines. I do that by picking some other point on the curve away from my point of interest. For example, if I pick the point 2, 2, I draw a straight line through that point. That is a secant line. I compute the slope of that secant line. In this case, I get 1. That was not a very good approximation to the slope at that point, but I refined my secant line approximation by picking points closer and closer to my point of interest. If I continue this process, I see two trends. I see the secant lines approaching the tangent line. I see the slopes of the secant lines getting closer and closer together and closer to the slope of the tangent line. However, this process will not lead me exactly to the tangent line or to the slope along the curve or the slope of the tangent line, because I can never take the straight line slope directly at the point minus 3. If I tried to do that, I would be dividing by 0. However, I can take the limit, if it exists, and when I take the limit of the slopes of those secant lines as x2 approaches minus 3, then I would get the slope of the curve at that point. Here is a graph of this process. The blue lines are the secant lines. The green line is the tangent line. The first secant line that I did had a slope of 1. The next one had a slope of 2. The next one 3. Then I ended up with a slope of 5. Okay. In the limit, these secant lines approach the tangent line, and the slopes of the secant lines turn into the slope of the tangent line, which in this case is 6. That is also the slope of the parabola at the point minus 3. So this process gave me the slope at one point along the curve. If I wanted to find the slope at another point, I would have to repeat this entire process. However, there is an easier way. By using algebra and exactly the same process, we can find an equation. The equation will give us the slope along that parabola. This is equivalent to having the equation for the slope along a straight line, only now we will have an equation for the slope of a parabola. Here is a process to use algebra to find the equation for the slope along the straight line. We start again with the idea of a straight line slope, because that's all we know. But now, instead of picking a specific point like x equal minus 3 and then finding the corresponding value of y, we let x represent any point in the domain of the function. The value of y at that point x would be f of x. So instead of writing x1, y1, we write x, f of x. Now we need another point that's some distance away. Instead of selecting a particular point, we just say it's going to be some distance h away from x, and we don't specify what h is. So we're doing all of this symbolically. Okay, so x2 is x plus h, because it is a distance h away from the original point x. And what is the value along the function at that time? Well, it is f of x plus h. So again, we're using the straight line slope formula. y2 minus y1 over x2 minus x1. Instead of x1, we use just plain old x. Instead of y1, we say the function at x. For point x2, y2, we use x plus h, meaning some point that is a distance h away from x. I don't care what it is. It could be 2, 10, 25, minus 3, doesn't matter. It's just some distance away from x. And then we evaluate the function at x plus h, and that gives us the y2. Now I take all this and substitute it into that equation for the slope. Okay, so here's the equation. Here's the equation for the straight line slope. For x1, I just put plain old x. My second point, x2, is the distance h away, so here it is, x plus h. y1 is the value at x, so here's the value at x. y2 is the value at the second point, f of x plus h. In the denominator, you get x minus x, so those x's are gone, and you end up with the difference quotient from chapter 1. Right. The idea in taking these secant lines was to make that second point closer and closer to the point of interest. Here, the equivalent of that is to let h get smaller and smaller. So what we're doing is taking the limit as h goes to 0. We don't have to let x2 go to x1 directly. We can just let h go to 0, and that second point will come in towards the first point. Here's the statement. The limit as h goes to 0 of m equals the limit as h goes to 0 of f of x plus h minus f of x over h. Obviously, we can't let h be 0 directly, or we would be dividing by 0, but the limit will take care of that for us. An example will make all this clear. We'll start again with our function minus x squared plus 6. The first point is going to be x and f of x, so we just use f of x as it is. The second point, x2, is going to be the distance h away from x, so here it is, x plus h. Don't care what h is right now. And now we have to evaluate the function at x plus h. Alright, just to make sure we all understand that, I'm going to go through that. Function evaluation means that whatever is in parentheses after the f, you substitute whatever that is for every occurrence of x in the formula. You use parentheses so you don't get sign errors and other errors. In this case, what's in parentheses is x plus h, so I have to change x squared to x plus h squared. Note the parentheses. To evaluate this, I've got to FOIL it. So I FOIL what's in parentheses and get this. Then I distribute the negative sign through and I get my answer. All this is just algebra, but just going over it so you'll do it right. Now I'm taking those results and putting them into that formula for the slope. So I need f of x plus h. Well, I worked all that out right here. Then I've got the h. Okay, put that down there. Fine. Now, here's the other tricky point. I have to subtract f of x. That means I have to subtract the original, all of the original function. So put that whole thing in parentheses. I think I said in chapter 1 that parentheses were very cheap and you can use them as often as you like. In fact, use them a lot. All right. If you don't, sometimes you get sign errors and other errors. Right. Now I have to distribute the negative sign through, carry out the algebra, and I get this expression. If you look back here, obviously the minus x squareds are going to go away, and the minus 6 will go away also. I think there's a sign error there. Let me check on something here. So it looks like there was a sign error right here. Okay. There should have been a plus 6. And the reason I'm showing this is because I would like you to see that, that there are ways to recover from errors. When you have a totally vanilla, perfect lecture on this internet, you don't see an error come up and see people recover from that. I think it's very important to see people recover from errors, since I assume that once in a while you might make some, and you have to learn that you can recover from them and go on. All right, so this should have been a plus 6. Okay, now I changed the minus 6 error into a plus 6. And you can see that the minus x squareds are going to go away, and that plus 6 is going to get subtracted off. The result is minus 2xh minus h squared over h. I can divide out that h, get an expression like this. Now I want to take the limit, and we're taking the limit as h goes to 0. Now there's no h in the denominator. We can just proceed, take the limit, and we find out that the result is minus 2x. This is the function for the slope any point along the curve. So if I want to know the value of the slope when x equals 0, I can just plug in for it and find out that that slope is 0. If I want the value of the slope when x is minus 3 as before, I just plug in a minus 3 and find out that the slope is 6. Or if I want to find out what the slope is when x equals 20, I just put 20 in this equation and find out the slope is minus 40. I don't have to repeat the whole process with the secant lines because we did that in abstract and used algebra. And now we have to digress a little bit to learn some notation. The letter M is reserved for the slope of a straight line. We'll still speak about the slope along a curve, but M is for the slope of a straight line. The more general term is the derivative. and it has quite a few different notations. The first one I'll mention is taking the function f and putting a prime after it. F prime of x. That means f prime of x is the derivative of f of x. Remember that when we've gone through this process, we end up with an equation. Okay, so this is the new equation, f prime of x. We can use the letter d for derivative. If we remember that the slope was delta y over delta x, we can change from this capital Greek delta to a lower Latin d and write the derivative like this. This is pronounced d by dx or df by dx, but it's a little bit of a confusion because d by dx is really an operator. It does not mean d times f divided by d times x. D by dx is an operator that means the operation of taking the derivative. Here's another notation. Instead of using capital Greek delta, sometimes this lower case Greek delta is used, often for partial derivatives. And you get partial derivatives, I think it's semester 3 of calculus. You probably see them in your application classes. Then there's another notation, and that is using dot. This is used mainly when you have a variable that changes with space and with time. The spatial derivatives are denoted with a prime. The dot denotes the derivative with, the spatial derivatives are denoted with prime. The derivatives with respect to time are denoted with a dot. So b dot, which equals dB by dt, means the time rate of change of the magnetic flux density. Again, it's the time rate of change for the dot. So if you ever see that, prime for spatial derivatives, dot for temporal derivatives. So now we'll use the new notation. So the derivative of the function f of x is df by dx, which equals the limit of the difference quotient. So in this example, here's my d by dx, which is the derivative operator. In parentheses, I write out the function. Okay, I can write it out, and then I say that derivative equals minus 2x. If I want to evaluate the derivative at a certain point, we have a formula for that. You write this derivative business here, df by dx. After that, you write the straight vertical line, meaning evaluated at, and then right at the bottom of the straight line, you write where you want to evaluate it. So this would be read df by dx, or the derivative of x, evaluated at x equals 2, equals, and then you plug 2 in for every x. In this case, there's only one x, so you end up with minus 4. Here's the result, and it looks, well, actually it is a graph that I was using earlier, but now the straight blue line does not mean a secant line. The red line is the parabola, f of x equals minus x squared plus 6. The blue line is the derivative. A derivative is a function in its own right. In fact, you could take its derivative as well. Let's see, here's the derivative, it's a function, and I can draw a graph of it. Getting an understanding between the graph of a function and the graph of the derivative takes a little bit of a while. So if you don't see this right away, just be patient, you'll get it sooner or later. Okay, look at this. The derivative of the function is 0 here. The slope is 0. Here, the value of the derivative is 0. Over in this region, for these negative values of x, the parabola has a positive slope. The derivative is positive. Here, get rid of this. Here, for positive values of x, the slope of the parabola is negative. Okay? And the derivative has negative values. So here's a summary of the process. It was sort of a 3-step process. We used the only tools that we had for computing the slope, which first was the straight line slope. Then we refined it. When we could no longer refine it, we took the limit to jump from the slope of nearby secant lines to the actual slope at a point along the curve. We repeat this process using algebra to get an equation for the derivative. The derivative is the slope at every point along the curve. This process doesn't always work perfectly. What can go wrong? The step that goes wrong is the limit. Okay, so since what is going wrong with the derivative is the limit, if we have a problem with the right and left hand limits and they don't agree, say we approach secant lines from the right and secant lines from the left, and we can't get an agreement on what they are converging to, then the derivative does not exist at that point. Those kind of points are corners or cusps. The absolute value function is a classic example of a function that has a corner. The absolute value of x is shown here in the red line. So it's a straight line down to x equals 0 from the negative values. Then it's another straight diagonal line for the positive values. Right at x equals 0, it has a corner. So if you looked at the slope coming down in this way, down from the negative values, they're all negative. In fact, they're all -1. If you look at the slope over here, as though you were taking a right-hand limit, all those values are +1. So there is no limit at this corner, therefore the derivative does not exist at the corner. The slope of, or the derivative of the absolute value of x is -1 if x is less than 0, and that's the blue line right here. It is +1 if x is greater than 0, and that's the blue line over here. But right at x equals 0, it is not defined. That's why it has those open circles there. Another reason that the derivative might not exist is that there's a jump discontinuity in the function. Of course, in a jump discontinuity, the right and left hand limits again don't agree. Derivatives also don't exist at vertical asymptotes. Remember, in limits, we accepted infinity as the value of a limit. Once we got to continuity, we would not accept infinity anymore as a criteria for continuity. And for derivatives, again, we do not accept the infinity. That means that if we take the limit of the difference quotient and we get infinity, we say no, that no derivative exists there. When you go to calculate the derivatives of functions, you basically just put them in that difference quotient and take the limit. Right? I'm going to walk through the process for a rational function just to show you some of the algebra involved. Okay, so here is the prototype rational function 1/x. I'll need the value at x plus h, and here's this value right here. Now I'm going to take the derivative, df by dx, so I'm taking the limit of the difference quotient. Okay. When I put all this together, I'm going to end up with fractions in the numerator. That is very bothersome. And here's a quick trick that you can always do. Just factor out 1/h. Then you don't have to worry about all that. So it's 1/h times f of x plus h minus f of x. Find your common denominator, do the algebra, and you end up with 1/h times minus h over x times x plus h. The h's cancel. This is very good because now when you take the limit, you're no longer dividing by h. And the result is minus 1/x squared. That is the formula for the derivative of 1/x. And here's the graph of 1/x, not defined, of course, at x equals 0. And the blue lines are the graph of the derivatives of 1/x. Notice that they're always negative. First, you might think that's a little surprising, but look at the curve 1/x. When you have all these, when x is negative, look at the curve. This red curve is decreasing. So its slopes are negative, so the slope of the derivative, or the values of the derivative, are negative. Over here, the slope is again negative because the function is again decreasing. Here are those negative values. So that's the process of taking derivatives. That is why we studied the difference quotient in Chapter 1. That's why we took limits in Chapter 2. And then we put them all together here. You want the slope along a curve that isn't straight. You use what you know how to do. That's a straight line slope. You refine it to the point where you can't refine it anymore. You see the trend in it. You take the limit. All those secant lines that you drew turn into the tangent line. The slopes of the secant lines becomes the slope of the tangent line. The slope of the tangent line is the slope of the curve at that point. Remember that there are a lot of sloppy definitions out there for tangent lines. Some say it's a line that touches the curve at one point. that doesn't make any sense at all. It has to intersect the curve at the point of interest and have the same slope as the curve at that point. That is a tangent line. Okay. Now we have a process using algebra, so we don't have to go through and draw those secant lines again. We do the same process, but we do things in general. And we do things in abstract, we end up with the difference quotient. So we're again taking the slope along that curve, using the difference quotient. We use the ideas that we know how to do, we refine them. At some point we can refine them no more, we take the limit. That limit will be an expression, will be an equation for the slope along that curve. You can evaluate it at any point and you'll get the slope at that point along the curve. Then we had notations. They involve things like df by dx or f prime or f dot, or sometimes using d's or primes. Okay, so there's quite a few notations. I'll try to vary it all over the place so that you'll get used to all of them, and you also can use all the different notations as well.